Boom. Hello and welcome back to Calculus 2. Today we're going to revisit exponential and logarithmic functions and stuff you learned in pre-calculus course. We're going to take a look at their definitions from calculus standpoint. So first, I would like to remind you that the number e is a number. It's not exponential anything. It's just a number. And if you put the exponent x, it becomes exponential function. This is the natural with a natural base e as a base. So this becomes a function as soon as you put x in the exponent. Now e squared is just a number and its derivative is 0 and its integral would be e squared x and so on. So you know all of the features of this function from your pre-calculus course. The domain is all real numbers. The range is only positive x values. The y-intercept is 1. No x-intercepts. Horizontal asymptote at 0. So everything that you learned holds, including the rules, right, of how to add the two and subtract the two and so on. What still might be not clear, and it should from Calc 1, is the definition of number e, which was the limit as n goes to infinity of 1 over n to the n. And if I want to create a function out of this, then I will have to have nx as the exponent. And this gives you e to the x. So I'm going to box these two because one is the limit definition of the number e and the other one is the limit definition of exponential function with natural base e. And now we understand that we can take the derivative of e to the x and get e to the x. Now you might ask why, and I will tell you now because there is a proof that utilizes the limit definition of the derivative with limit h goes to 0 f of x plus h minus f of x over h. But there is a far more elegant proof in coming up in this class later on with power series. So I'm definitely going to show you that one. So just, you know, you accept this for now, and then because I didn't show you any proof for it, and you probably accepted it for Calc 1 as well. And then by the end of the course, you will know a really cool way to show that this is true. But then you might say, well, e is not the only number that could be base. We can have any number as a base. So we have that the derivative of a to the x, a stands for any number, right? So the derivative of this would be ax times ln a. But then you would say, well, these are just basic functions. What happens if I have e to the sine x, or 3 to the sine squared x, or something like that? So how do I deal with more complex situations? Well, looking at the e, if you have e raised to some kind of a function, you will just unleash the chain rule. So it's the standard Calculus 1 procedure. you copy the entire e to the f, and then you multiply it by the derivative of f as a chain. So now I want to know what is the derivative. Technically, I call this the boss equation, because this equation allows you to look at any possible combination. In this case, you can have your 5 raised to sine squared x, and you will be able to take the derivative because of this. So what do we have? Well, first of all, it's exponential, right? So we have to copy the whole thing, times the exponent, the base is not e, so we have to have the ln a there, and also the chain rule, which is f prime of x. So this is the one that I'm going to box, because this is the boss equation here. This covers any possible case of exponential that you can have. And you can see quickly that if you want to use it to calculate e to the x, you can, because if a is e, then that's e, and that's ln of e, and ln of e is 1, so that dies. And if this is x, then this would be x, and you get your e to the x. And then this would be the derivative of x, which is 1, so you get e to the x times 1 times 1, right? So it collapses onto this formula. So this is the boss equation, and all of these are special cases that we remember because we can, I guess. We have a lot of memory. This is the one that governs any possible case that you can get. So I want you to use that equation now and practice on, let's see. What's a good base? Chuck, what's a good base? 47, okay. And what's the good exponent function?
X squared.
X squared, all right. That's okay, I picked the next problem. Oh, yeah. For this, right?
Yep. I'm actually going to get something way harder than you guys.
Okay. All right, so this exercise is fairly quick, right? So we go Control C, Control V, and then ln 47, and then times the derivative of x squared is 2x. All right, so let's see. Kevin has some challenge in mind. What do you want?
It's 5, sorry, it's going to be 5 on the upper end, sine, parentheses, 2x, parentheses, 5.
Over here?
Yep.
Or over here?
Right there.
Like this?
Yes.
Nice. All right. Courtesy of Kevin. Enjoy.
I think it's going to be pretty easy for everybody.
We're on 95. Fine. You have to switch one. Yeah, this is the evil problem. You have to start with a cosine. It's not have a triple chain rule over here, right? 1, 2, 3 functions. So, but you could hack and just do this to the 5th power, get a 32 x to the 5, right? Then you can go from there. It'll be 1 chain rule less. So to solve this problem, I'm not going to have enough room to write out the derivative, so we start a new line. It's 5 sine 2x to the 5 times, take care of ln 5 right away, and now times the derivative. So the major function is sine, so its derivative is cosine of 2x to the 5 times the derivative of 2x to the 5 is 5 times 2x to the 4th, and then the derivative of the inside, which is 2. See? Beautiful. So to simplify this, you can put the constant and the function in front. So you have 10 ln 5, and then you have 2x to the 4, and then you have your cosine of 2x to the 5, and finally times the exponential 5 sine to a 2x to the 5. That's really cool. Two times 5 is 10 in front.
Let me ask you, don't we use this like after? Never mind, I remember. So it says like the chain rule pretty much.
Yep.
Does that, I forgot you had to actually bring the 5th power with you.
Yep. So you have 3 separate functions, so that means 3 chains. All right, time for logs. A log, yes. All right. First of all, logarithms are mathematical operation that happens between 2 numbers. Logarithms are not functions. Just like trig, sine and cosine are not functions. It becomes a function when you get x involved. You know how 2 plus 3 is 5? And then you can go 5 minus 2 is 3, and 5 minus 3 is 2. So you have addition and the opposite operation, subtraction, which are all operations between numbers. And then you have 2 times 3 is 6, and then 6 divided by 3 is 2, and 6 divided by 2 is 3. So again, opposite operation to retrieve all of these numbers back. And then you have 2 cubed is 8, with the cube root of 8 being 2, and log being the one that extracts 3. So log is just operation, just like addition or subtraction, except it operates differently. And it also suffers from this, the fact that it's the only mathematical operation that we see here that doesn't have a symbol to it. It has letters, right? So you kind of want to treat it differently, but you shouldn't. It would maybe be better if we had like 2 plus 3 is 5, then maybe logs would have a better placement in the world. It wouldn't be discriminated against as much. But such is life, I guess. So logarithms are simply computing a value given two values just like any other. And then we decide to place x in it, and then it becomes a function just like any of the other ones. If you had, instead of 2 plus 3, you had 2 plus x, you call that linear function. Or if you had 2 times 3 written as 2 times x, it's also a linear function, right? 2x, but it's a function. So as soon as you involve x, it becomes a function. And then you have the entire pre-calculus spiel on that. That is, well, it's inverse of exponential. It has the domain only positive numbers. The range is all real numbers. The x-intercept is at 1. Vertical asymptote is at x equals 0. So everything you learned in pre-calculus follows at the moment when you place the x and create a function there. So now we are going to define the natural logarithm function, the ln. Oh, first, before I go do definition, so log a of x, this is any base a, and we have the two special cases that carry lazy notation. If you have log x, that is actually log base 10x. So in sciences, you will find log base 10 very frequently. If you are calculating the intensity of the sound on the decibel scale, you are calculating the strength of the earthquake related to pH calculations in chemistry and so on. So there's a lot of calculations in sciences that are using base log 10. So we have a lazy notation for it. If there is no base, it's just log, the base is 10. And then the next one is the ln x, which is the natural base. So writing ln x is whole 2 characters shorter than writing log base ex. So, and it models so much of our everything we touch technically, that it's much faster to write ln x than to write log base ex every time. So now we are able to define the this ln x using the integral 1 to t of 1 over t dt. So this is the definition, right, for all, sorry, 1 to, not t, 1 to x. So just quickly to outline this, integral 1 to x of 1 over t dt would be ln absolute value of t computed from 1 to x. This is like a little proof or whatever. And it's ln absolute value x from, sorry, minus ln of 1. Now ln of 1 is 0. So it just becomes ln x for all x is larger than 0. So that's a little kind of proof derivation there that this is a good definition in terms of calculus. It's a good definition for ln x. Now, as I said, we don't do integral of ln x. That's after test. So that's tomorrow? Wednesday. So Wednesday we do that. Now, you have properties of logs, and you can actually run this against all of those properties that multiplication, the argument goes, the sum is logs, and all of that stuff that you learned. All of those formulas would actually work if you use calculus definitions. They have to. The book outlines those proofs if you're interested. What we are interested here is to talk about the derivatives of logs, because we know that so far. Oh, I skipped integrals of e. I skipped integrals of e. I have to do that afterwards. The derivative of ln x is 1 over x. Very good. So now let's make it more interesting. What is the derivative of ln of f of x? Beautiful. So you take the argument as is, and you copy it there, and then you take its derivative in the numerator. It's very systematic, very, very simple. So you copy the argument exactly as is, and then you just find. Good. But wait, we can have any base, right? We can have any base. So what's the major formula? Log any base of a function. Anyone?
Oh, isn't it the same thing but times ln? Or no, times
You're close. Yes. Nice. So it's going to be the same as up there. So it's going to be f prime of x over f of x, but there's going to be ln a in the denominator. No, not denominator, numerator, because the denominator is for the for integrals. For integrals, it goes in the numerator. Denominator. Yeah, whatever. So this is the major formula, the Boss equation. So let's find the derivative of log base 7 of tangent squared x, because we can. So we write the function as is, tangent squared x in the numerator. Then we have 2 tangent x, and the derivative of tangent is, very good, times ln 7. So one of the tangents dies, and we are left with 2 ln 7 times secant squared x over tangent x. We can simplify this more, actually, right? Because secant is 1 over cosine squared over there, and then you have tangent over a sine over cosine. So one of the cosines will cancel, but we're not going to get far. So that's it. And now just to quickly address the integration. For exponential functions. So integral of e to the x dx is
e to x over x. Yeah.
no. Integral of e to the x is
E to x over x, like underneath it.
nope. Plus c. There we go. Yep, plus c. What's the integral of a to the x dx?
A to x on ln of a.
Yes. So it's going to be a to the x over ln a plus c. Nice. Good. And that's that. Done. So the next section is section 6.9, when we do word problems. Again, from pre-calculus, these are growth and decay problems that involve exponential and logarithmic functions. Restart the stream.